hear me? That sounds good. So I'd like to talk about terrestrial gamma ray flashes and their connection to lightning. This is a effort of a large group of people on the Briggs1.mpg team. You see their names here, and I hope it becomes an expanded effort with more involvement from the lightning researchers. So first, just let me say a little bit about what a terrestrial gamma ray flash is. This shows some observations from our detectors on the gamma ray burst monitor. The horizontal scale is time, with each tick mark being a millisecond. And the vertical scale is energy, as Dr. Ravkoff explained. X-rays and gamma rays we refer to as energy, going from 300,000 electron volts, keV, all the way up to 30 million electron volts, MeV. And the points here are individual photons measured by our detectors. So we have a burst of photons lasting for well under a millisecond, so a flash of gamma rays. And this came from the Earth, hence a terrestrial gamma ray flash. And that's the phenomenon I'll be talking about today. These have been observed by about 4 or 5 instruments now. They were discovered in the early 1990s with the BATSI instrument, Burst and Transient Source Experiment, on the Compton Gamma Ray Observatory. So far, they've been observed by astrophysics experiments. There hasn't been a dedicated terrestrial gamma ray burst experiment yet, one designed for the purpose. The instrument that's observed the most has been the RHESI Explorer, which was designed to observe solar flares. It has a sample of 1,000. Also being observed by the Italian gamma ray instrument Agile. And now with the gamma ray burst monitor, GBM on Fermi, that's an instrument that I, with a large team, helped design and build. And as the name says, it's another astrophysics instrument. It was designed to look upward and observe gamma ray bursts. But we're fortunate it can do other scientific goals, solar flares, and we're going to talk about today. It has such a wide field of view that even though it's designed to look upwards, we can also see these flashes of gamma rays that come from underneath, from thunderstorms. Let me next show you what the instrument looks like. This is a picture of the Fermi spacecraft sitting on top of the Delta II rocket just before launch. For them to do their final testing, they put a little building around the top of the rocket so they can check out the instrument. You can get a sense of scale from some of the people that are here and the little protective chains. It's a very large spacecraft, several meters in dimension each way, thousands of kilograms. This is the main instrument up here on top. You can't see very much of it because it's in a protective shielding. That's the Large Area Telescope, which has contributions from many nations, including Japan. Its purpose is to observe high-energy gamma rays from about 50 million electron volts to 300 billion electron volts and above. Our instrument, the Gamma Ray Burst Monitor, has these detectors, a group on this side and a group on the opposite side that you can't see, 12 detectors in total, 14 detectors in total. There are 12 sodium iodide detectors. You see here 2 clusters of 3 each, and there's another 2 clusters on this side. And they're pointing in different directions in order to view as much of the sky as possible, pretty much the entire sky. It's not blocked by the Earth. And those detectors are observing from 10 kilo electron volts, 10,000 electron volts, to 1 million electron volts. And then we have this large bismuth germanate detector, BGO, to observe from 200 keV, 200,000 electron volts, to 40 million electron volts. And that turns out to be a nearly ideal range to observe TGFs because they send off the bulk of their emission in that range. All of these detectors are scintillation detectors. They're inorganic crystals, transparent crystals, and when an X-ray or a gamma ray enters those crystals, they interact by photoelectric effect or pair production or Compton scattering and create ionization. And as the ionization of the atoms ends and the electrons return to their ground state, it emits optical photons, which are collected by these photomultiplier tubes, for example, at the end of the two ends of the VGO crystal, or you can just see it here at the ends of some of these sodium iodide detectors, and convert it into electrical signals, which is how we measure these X-rays and gamma rays. Let's return back to the science. This shows you some of the first evidence that told people that TGFs are connected to thunderstorms and lightning. This is from the GBM data, but this was recognized even with their discovery with BATSI. The bottom figure shows you a map of lightning flashes as measured with the lightning imaging sensor of NASA. And you can see the hot spots on the continents and near the coastlines, and not so much lightning in the oceans. And the upper figure shows you measurements of TGFs, the location of the Fermi spacecraft when we detect TGFs. And you see a very similar pattern. We're unfortunately not able to observe this region because of the radiation belts. We don't observe most of South America, but we see concentrations of TGFs in Central America, Africa, and throughout Asia, which follows fairly closely the pattern of thunderstorms and lightning. It shows there's a correlation between this phenomena. It doesn't follow exactly. There's a really very strong hot spot of lightning that doesn't correspond exactly to the concentration of TGF. So somehow lightning in Africa doesn't make TGFs as effectively as, say, lightning in Central America or in Asia, which is an interesting subject that's not understood yet. So how do thunderstorms make lightning? There's a basic theory that's been developed over the years that gamma rays originate from Bremsstrahlung emission of electrons. Bremsstrahlung is German for breaking radiation. Whenever a charged particle accelerates, it emits radiation. In this case, we have energetic electrons that, when they pass through near an atom, are de-accelerated or they're accelerated and change their paths, and they emit X-rays and gamma rays. We believe that the electrons are accelerating strong electric fields we know are present in thunderstorms. So that's the basic concept, but there's a lot of details to that which go under the names of relativistic runaway electron avalanche model, which is the process for getting the numerous electrons we need, and that basic process doesn't even produce enough electrons because TGFs are so intense, and so there's an augmentation of that which is called relativistic feedback that increases their multiplication. When you think about it, that first figure I showed you that had that this figure here that's got something like 200 photons, that's observed over a detector that's this large, actually two detectors this large, 200 square centimeters, 500 kilometers from the thunderstorm. So that implies a very high flux of photons, and a very large number of electrons had to be present generated by the thunderstorm to produce that kind of intensity. So